All right. Are you guys with me?
Evet hocam.
Okay. So now we will take a look at something called direct synthesis. Okay, it's a different way of designing controllers that different than what we have seen in 302. Quite different actually. So let's say EE402, 407, week 11 continued. Okay, so we will take a look at a method called direct synthesis, and then we will proceed with something called the internal model control, or IMC. So internal model control is a more advanced version of direct synthesis. So we need to first take a look at direct synthesis. Then we will cover internal model control, and then this will give us many of the PID formulas that we have, in particular for the FOPDT model. Okay, but we will see that direct synthesis actually can be applied to finite dimensional, that means regular linear systems, but we need the Pade approximation in order to derive IMC formulas, and these are the ones that I have given to you as design formulas for the FOBDT plant. Okay, sometimes this is also known as model-based design because it heavily uses obviously the plant model. Okay, by the way, next term Klaus Hoca's lectures, for those of you who are in the control option, you will maybe take Klaus Hoca's lectures, Klaus Schmidt's fourth year course. That's going to elaborate more on this idea of direct synthesis for a single input, single output system. Okay? So, by the way, let's start with a note. Okay, this method actually is general and may be used to design controllers other than the PID range of controllers, PID class of controllers, but this will be, that means the PID range of controllers will be our focus. Okay, so we will not too much wander around into non-PID controllers, but as you will see, the method does not make an inherent assumption about a PID controller. Okay, so let's see what we are talking about. Okay, consider our single loop feedback control architecture. Single loop. By the way, we call this a single loop because at the end of the term, I will discuss multi-loop systems having more than one control loop. Okay. This is a single loop feedback control architecture. And as you know, this is consisting of a reference signal, R of t, which actually the difference, the error signal, feeds a controller that we call GC of S. Often this controller drives an actuator, GA of S. The actuator drives the plant, GP of S. And the plant generates a response. The response is measured by a measurement system with a model GM of S, and then this comes back to the comparator device. Okay. Usually we simplify this model by simply considering all this thing basically as the plant model as seen by the controller. Remember this wire out to wire in concept. Okay, we incorporate this as simply collecting all of these modules together in the form of a single transfer function, which we often call the plant transfer function. Okay. All right. So for simplicity, we will again assume that actuator and measurement models are all combined into GP of S, so that we have GA of S equals to GM of S is equal to unity. Okay, so we assume them to be unity transfer functions. Okay, now what is the overall transfer function of this system? Overall TF. We know how to derive that. Okay, let's call this T of S. This is the output over the reference R of S, and that is given by simply GC GP, and I am dropping S dependence, but it's inherently there. I'm going to do some calculations, so I don't want to write S every time. So please assume that the S dependence is there. Okay, so 1 plus GC GP. Okay, this is your this is something that you know from 302 and 407. This is something that we use all the time. The overall transfer function in terms of what is in the control loop. Okay, now the idea is this: can we express the controller GC of S in terms of the other system components? Okay, the simple answer is yes, but there are some issues that needs to be considered, and we will come back to them in a minute. Okay, now one thing that we need to identify is that in order to be able to do that, we should first specify what is the overall transfer function that we need. So without specifying T of S, we cannot express the controller in terms of the other components, because T of S is part of that system. Okay, so suppose we define or specify what type of T of S we want. In that case, we can attempt the required controller, attempt to find, let's say, the required controller GC of S to achieve that. That is why this is called a direct design. Okay, the idea is very simple. The idea is how I specify, how about I specify T of S and simply extract GC of S in terms of these other system components. Okay, so let's try to do that. So we start with T equals, again, remember we have S dependence on all of these functions. So GCGP over 1 plus GCGP. So I can simply write down T plus T times GCGP on the left hand side is equal to GCGP on the right hand side. So that means I have simply T is being equal to, right? We have GCGP minus TGCGP. Let me take this into GP parentheses. So T is equal to GCGP 1 minus T, all of them functions of S, right? And therefore I can simply write down GC of S now as a function of the rest, 1 over GP of S times T of S over 1 minus T of S. Okay? So let's call this equation star if we need it. Okay? So we have expressed GC of S in terms of the desired overall transfer function T of S. All right? Now we need to make some observations. Okay? Let's call them notes. Okay? There are some important things that we need to observe here. Notes. The first thing is that you see that GC of S, basically GC of S depends on 1 over GP of S. So it's like an inverse, okay? It is as if we are inverting the plant. So this obviously has implications, right? For example, poles of the plant are basically related with the zeros of GC of S, and similarly zeros of GP of S, zeros of GP of S are related with the poles of GC of S. Okay? For example, there are many things to think about. For example, if you have any unstable zeros of the plant, that's not a problem for the plant, but they will become the poles and unstable poles of the controller. So the controller itself may become an unstable system. Okay? So that's something to think about. Right? So another note, ideally we would want, what would you want ideally for T of S to be? What is the ideal T of S? What do you think? Remember, T of S is the overall system transfer function. What is the ideal transfer function?
1, I guess.
Well, yes, it is 1. It's basically a step response, right? As soon as you have a 1 in the reference, you want 1 as the overall transfer function. You want everything to be transmitted one by one to the output, right? If the reference goes to 1, you want the output to go to 1. If the reference goes to 0, you want the output to go to 0. So the ideal transfer function is equal to 1. It's the direct transmission of the reference to the output. Okay? So that's correct. So we want T is equal to 1. Okay? So we can call this the output follows the reference, right? Follows the reference. Now take a look at the expression that we have derived. Is this possible? Can we achieve that?
No.
Why not? So when I say T is equal to 1, what I mean is T of S is equal to 1, right? It's a function. So yes, right? So this equation tells us that if T of S was equal to 1, in fact, the controller would need to have infinite gain, because the denominator would go to 0. If the denominator goes to 0, basically this whole thing would go to infinity. That means the controller would need to have an infinite gain in order to be able to achieve that. So that shows us that this is not possible. Okay? So we see from star that this is not possible. This is not possible. As it would need infinite gain for the controller. Okay. Now let's see whether there are other implications as well. Okay. Now let's see whether t can actually be a constant. Okay, not 1, but can it be a constant? Okay. So can, let's say another note, can t of s be a constant? Now let's see. Now we need to have, now t, remember, is y over r. It cannot be arbitrary because the closed loop transfer function, the closed loop characteristic equation needs to have a solution or some solutions for some s, because the closed loop system needs to have certain poles, a closed loop behavior. There needs to be some poles of the closed loop system, and these are the solutions to the characteristic equation. Remember what characteristic equation is. So Q of s equals to 0 needs to have a solution. That means 1 plus GC of s GP of s equals to 0 needs to have a solution. Okay? And if we write this down, this is 1 plus, right? Simply T of s over 1 minus T of s is equal to 0. Okay? So that means simply 1 minus T of s plus T of s over 1 minus T of s is equal to 0. Now T of s is cancelled out in the numerator. Now if T of s is a constant, this equation doesn't have any solution. Okay? So this does not have a solution for T of s is equal to Kc or K. Okay, sorry, K. Okay. So that means T of s cannot be a constant, and that means no instantaneous response. Okay, so there needs to be a time constant. You cannot have an instantaneous response even if that response is not unity. Even if you have a positive or larger than 1 or smaller than 1 gain, you can still cannot realize this and obtain a closed loop overall system with a certain response. Okay? Now let's try to see another realistic response, and let's see whether we have a solution for that. Okay? So assume we start with with a realistic overall response. One such realistic response is a first order response, right? Let's assume that we specify T of S to be equal to 1 over 1 plus tau CS. So we are saying that, okay, I want the overall system to have a first order response. So it's gonna converge to the reference, but with a time constant. Okay, so first order response with unity gain. That means you don't have any steady state error. Okay, no steady state error, because your reference, remember, is a unit step function. So with unit or whatever step function you have, you will converge to that final value with unity gain. Okay, and time constant tau c. Now tau c is a design parameter, right? Design parameter that specifies the desired response. Let's say speed. Okay, obviously the fact that we specify a first order response is also part of the desired response. Okay, so we make a decision that we want a first order response, and we also make a decision on how fast that response should be. Okay, so this is a design parameter. Okay, remember, a first order response is where you basically have, once you have your reference like this, your response will basically exhibit something like this. Okay, sorry about that, wrong key. And the time constant, right, specifies where this tangent will intersect the desired value. Okay.
Hocam bir şey sorabilir miyim?
Go ahead.
Bu üst tarafta anlamadım ben. Niye bu constant olamıyor T of S? Çünkü Planck'in 1 bölüsü olursa sanki oluyor gibi duruyor. Yani oradaki reasoning'i anlamadım ben açıkçası.
Şimdi şuraya bakarsanız şu denkleme. Şimdi buradaki denklemde şöyle bir şey elde ediyoruz biz. 1 bölü 1 eksi TS eşittir 0. Doğru mu? Şimdi bu denklem çözülebilir ama ancak t as a function of s olursa çözülebilir. Eğer t constant olursa 1 bölü 1 eksi k eşittir 0 olmuş oluyor. Buna bir çözüm bulmak mümkün değil. Dolayısıyla t of s'e bir constant veremediğimizi gösteriyor.
Şey anlamıyorum hocam. Niye bunu 0 eşitlemeye çalışıyoruz denominator'ı?
Çünkü sonuçta biz overall sistemimizin bir takım pole'ları olmak zorunda. Yani bir davranışı olmak zorunda. Pole'lar da biliyorsunuz by definition characteristic equation'ın kökleri. Dolayısıyla characteristic equation'ın bir çözümü olmalı bazı s'ler için. Tamam? T of s bir constant olduğunda characteristic equation dediğimiz polinomun kökü kalmıyor. Yani hiçbir kökü yok, çözüm yok. Dolayısıyla bir behavior'dan, bir işte ne bileyim ben, hani pole'lardan bahsetmek, bir behavior'dan bahsetmek mümkün olmuyor.
Yani bana şöyle geldi, hani pole'lardan bahsetmek istediğimiz için bu duruma çıkıyoruz. Ama hani bahsetmesek o zaman şey yapabiliyoruz, bir constant transfer function elde edebiliyoruz. Mesela sistemimiz 1 bölü s olsun. Biz de s koyarsak oraya, daha doğrusu 2s koyarsak ya da 1 bölü 2s koyarsak bir transfer function elde ediyoruz constant bir şekilde.
Evet, ama işte bunların hepsi sonuçta şeye karşılık geliyor. Yani bir ne diyelim non-causal bir şeye karşılık geliyor. Yani instantaneous bir response anlamına geliyor. Yani bir ne diyelim hani gerçek fiziksel bir sistem olmaktan çıkıyor yani.
Anladım.
Tamam. So let's see what we have. Actually, this is not completed yet. So let me, in fact, it's going to be kind of clearer when we put this kind of a more realistic overall response in place. Okay. And we will see that we still have some problems. Okay. So the controller in this case will be 1 over GP of S times, remember, T of S over 1 minus T of S. So here is my T of S, 1 over 1 plus tau CS over 1 minus 1 over 1 plus tau CS. Okay? So that basically simplifies to 1 over GP of S times 1 over tau CS. Okay?
Hocam ben şey sorabilirim, azıcık geriden olacak ama eğer karakteristik equation'ın çözümü olmazsa, hani biz de root 9'da da şey yapıyorduk ya, mesela hiç zero'su yoksa, sadece polu varsa diye düşünüyorduk. Biraz karıştırıyor gibiyim de. Yani eğer solution olmazsa ne oluyor karakteristik equation'ı tamamen?
Ya buna çok tatmin edici bir cevap veremeyeceğim herhalde. Yani arkadaşının sorusuna da çok tatmin edici bir cevap veremedim. Ama sonuçta bunlar hani conceptually hep şeye geliyor. Yani sonuçta gibi düşünün. Hani hiçbir fiziksel sistem aslında anlık, yani instantaneous bir cevap veremez. Çünkü causality'ye aykırı. Yani herhangi bir sistem, sonuçta düşünün, loop'un içinde bir plant var. Bu plant'in bir sonuçta bir response'u var. Siz içinde bir response olan, yani finite bir response gösteren bir plant içinde olmak üzere mesela belli bir hızla cevap veren bir plant içeride kalmak üzere siz tamamen hani instantaneous bir response üretemezsiniz. Yani causality'ye aykırı bir şey olmuş oluyor. Tıpkı hani aslında bu şeyde de var. Mesela S tek başına derivatif gerçekte unimplementable bir şey. Yani fiziksel olarak mümkün olan bir şey değil. Niye? Çünkü derivatif dediğimiz şey aslında by definition, yani derivatifin matematiksel definition'ı aslında non-causal bir definition. Niye? Çünkü bir limit olarak tanımlanıyor ve limit işte fonksiyonun t artı delta t eksi fonksiyonun t'deki değeri bölü delta t. Fonksiyonun t artı delta t'sine ihtiyacınız var. Aslında bu causal bir işlem değil gibi. Ama dediğim gibi yani çok da tatmin edici bir cevap değil. Ama şu anda verebileceğim bu kadar yani.
Hocam ben küçük bir şey soracağım. Biz mesela devre dersinde bu dirençli de yani resistif devreleri anlık respons veriyor diye kabul ediyorduk ama o bile aslında gerçekçi bir yaklaşım değil mi? Çünkü kablolar var. Kablo belli bir hızla iletecek.
Aynen öyle. Yani biz orada lumped parameter approximation'ı sayesinde rezistans dediğimiz ideal elemanın algebraik bir şey olduğunu kabul ediyoruz. Ama gerçekte input'uyla output'unda arasında tamamen algebraik bir ilişki olan aslında hiçbir komponent yok. Çünkü hepsinin içinde aslında bu lumped parameter approximation'ın dışında bir şeyler oluyor aslında. Dersin devamında bu lumped parameter approximation'ını kaldırarak distributed sistemlerden bir miktar bahsedeceğiz. Orada biraz daha sizde tabii ki geçmişte mesela transmission line kavramı mesela lumped parameter approximation'ın dışında bir kavram. Neden? Çünkü bir transmission line lumped parametre olarak aslında sadece bir kablodan ibaret. Öyle değil mi? Ama düşündüğünüz zaman uzun mesafelerdeki kabloda aslında rezistans ve kapasitanslar olmaya başlıyor. Dolayısıyla kablonun üzerindeki voltaj devre teorisindeki gibi her yerde aynı olmuyor. Yani kablo tek bir node olmaktan çıkıyor. Hem zamana hem de mesafeye bağlı voltajlar oluşmaya başlıyor. Dolayısıyla bir variable, devre variable'ı mesela voltaj, sadece zamanın bir fonksiyonu olmaktan çıkıp v of t and x olduğu anda, yani sizin voltage variable'ınız hem zamanın hem de mesafenin bir fonksiyonu olmaya başladığı anda işte o zaman sizin bir distributed parameter bir modeliniz olmaya başlıyor. Lumped parameter modeller differential equation'larla gösterilirken distributed parameter modeller partial differential equation'larla gösteriliyor. Yani derivatifleri sadece zamana göre değil, mecburen hem zamana hem de mesafeye göre almak zorunda kalıyorsunuz. Tamam? Başka soru var mı? Okay. So let's go with this for now. Okay, bear with me. So GC of S for this case is equal to GP of S times 1 over tau C of S. Okay, so this still preserves the basic property that the poles of the plant becomes the zeros of the controller. The zeros of the plant becomes the poles of the controller. So that, for example, unstable zeros, which were not a problem before for the plant, now starts becoming a problem for the controller. Okay, and there are other issues as well, as we will see. For example, we will see that there can be mathematical cancellations when we are calculating the controller, but these are cancellations, pole zero cancellations, that are mathematically valid, but in practice, they may lead to other issues as well. So we will discuss those in a minute. Okay, so what is the, with this controller, so with this controller, the closed loop characteristic equation, that means the closed loop poles of the system, right? Q of S is equal to 1 plus GC of S, GP of S. That is equal to 1 plus, right? You have GP of S over GP of S times 1 over tau S. Okay, tau CS, sorry about that. Tau CS. So you see that there is a cancellation occurring here, so that you have tau CS plus 1 is equal to 0, and that gives us the single pole of the system, which is 1 over tau C minus 1 over tau C. Okay, this is in fact the design criteria, right? We started from this pole, and this is just to verify that we obtained this pole, but again, mathematically ideal operation is happening here, right? Mathematically ideal cancellation is happening here. So what does that mean? For example, if you have any small mistake between the actual plant model and the plant model that you use for designing the controller, this cancellation may lead to other issues. Okay, that means you will not have exact cancellation, and that may lead to issues. One issue we had discussed, right? For example, if you're canceling an unstable pole of the plant, but you fail to cancel that pole because you have a small deviation from the pole, remember in the root locus, that's gonna basically squeeze you between this unstable pole and the zero that failed to cancel that pole. So for all ranges of the gain, your system will become unstable. You remember that discussion? Okay, so it's like this, right? Example. So here is an unstable pole unstable plant pole. Okay, so the 0 here, that's a failed cancellation. So immediately you will have root locus squeezed here, right? Root locus squeezed into unstable region. Okay, so you cannot make this system stable, because for no value of the gain you can obtain a stable system. It's just within this tiny interval in the right half plane that's gonna happen because of a failed cancellation. So this is one of the kind of implication of this ideal cancellation. But still, this direct design is based on this idea. But for example, if this cancellation was happening on the left half plane, that's not that much of a problem, because yes, you will have some change in where the root locus will be squeezed to, but the system will still work. It would still be a stable system. Okay. All right. Another note: since tau c is our design parameter, it seems we can select it as small as we want, this means a faster closed loop system. In practice, this is not possible because gain of GC will become very large and will saturate the actuator, right? So you see that tau c is here at the denominator. Sorry, where is it? Yes, here you see that tau c is at the denominator. So if you make tau c very small, the gain of the controller will increase, and the gain of the controller has an effect on the signal going to the actuator. If you have a very, very large gain for the controller, that's going to saturate the actuator. So the system will become nonlinear and it's not going to work. This is the same as selecting closed loop poles that are very far away from the j omega axis. Okay? You know that the farther away from the j omega axis, the faster the system and the more stable it is. But in practice, this would need a very large gain for the controller, and that's going to eventually saturate the actuator. Okay. Also, another note, which we have discussed, unstable zeros of the plant become unstable poles of the controller. So controller may become unstable. Now that's also an interesting concept, because it's like part of the system becoming unstable. What does that mean? That means that overall system behaves in a stable manner, but the controller becomes unstable, meaning its output may diverge. If the output diverges, for example, it becomes very large, it's going to saturate the actuator. if the actuator saturates, the model, the ideal mathematical model will no longer be valid, so the whole system will fail. Okay? If you remember state space, it is also related with the observability concept, right? It's like there are some states that are becoming unstable. Let's say state 2 is becoming unstable, but the output of the system is measuring only first state. So the output does not show the unstable state, but that doesn't mean that the system will work, because it's going to blow from the inside. Some states will become very large. That's going to eventually burn something, blow something up, and the system will fail. But the interesting concept is that you will not see this at the output. Why? Because if you calculate the overall transfer function appears stable. Okay? Do you guys follow my discussion? All right. What's the time? We have a minute. So I have a very simple example, but I'm gonna put this example on the web for you. Okay, and then we will continue with a bit more complicated example tomorrow. Okay, is there any questions?
Ben şey sorabilir miyim hocam?
Go ahead.
Sabit olamaması transfer fonksiyonu. Hocam
Cool.
aslında bu şimdi biz controller'la ya daha doğrusu transfer